Hi there. In this lesson, we are going to take what we know about sets and relations and move that into a super important concept for math, which is functions. And if you haven't heard the word yet, you will, and you will hear it from now probably until when you are done with math. Please give this video a thumbs up if you find it helpful, subscribe for more math help, comment to engage, and check out the practice set and some of the other videos on the channel. Now, we are going to start with what we covered last lesson about relations and sets. So if you jumped into this video and you have not watched that other lesson, up here in the upper right, I am going to link a card, okay, to that lesson. I need you to click here, okay, stop this lesson right now, go click on that, watch that, and then come back and join us for this one, all right? So for those of you that are here or returning from watching the other video, we're going to recall what we covered last lesson about relations. A relation is just mapping one set of numbers onto another set of numbers, okay? And no pattern required, although we're very quickly going to start to home in on what some of the patterns are that we might see. But here we've got our first set, which is the set 1, 2, 3, and it is mapped onto the set 4, 5, 6. Typically, the first set, we call that like our X set. There's actually another vocab word for that we will introduce in this lesson, but that's our X's. That's our originating point. You might hear it as the input. Okay, if you think about, you put like something into a machine. Okay, and so we're going to put in a 1, a 2, a 3, and the Y values over here. The second set is the Y values, and that's typically considered our output. And you can see that each element in X is mapped over to some element in Y. Now, relations can be displayed using ordered pairs, which is kind of cool. So we know that we have these ordered pairs from previous study in algebra, where you have like an X and a Y. And since we have assigned the X's to be our originating set, we can look at the mapping and see, well, what does that X go with? So we can see that 1 maps to a 4. We can trace this arrow to see that 2 maps to 5 and 3 maps over here to 6. Okay, and so we've got this idea of relations and we're mapping one set onto another. Now, functions are a specific kind of relation, and the vast majority of what you cover in your math classes is going to be functions. Not everything, okay? There are some relations that are not functions that do get highlighted. Typically, there's one that you'll probably see in a geometry class, and then the others might crop up in an algebra 2. For me, it was algebra 2. A lot of times it's pre-calculus. You might see some other things that are not functions. But most of what you study in your math classes are going to be functions. So we really want to have an idea of what functions are. Now, right here, we've got essentially our definition of functions. Functions are a specific type of relation in which each X value maps to only one Y value. Okay, and I would pause the video. If you've got a notebook handy, pause it and write that down. Okay, what I started there. Hope you did that. Hit pause and wrote it down. Each X value maps to only one Y value. Now, this is a function. If I look at my 1, there's only one arrow coming off of that 1. So that 1 in my X values is only going to one thing. I only had one arrow. I mean, now there's 2 because I had the purple and I wrote the red over it, but here we could go delete mine. All right, and one arrow coming off of the 3. And so each of my X values is only going out in one direction. This is going to be easier to see if we display our sets vertically instead of horizontally. And it's not that there's anything wrong with doing it horizontally, but if you look at like where our eyes have to go, we've got to trace these arrows through a bunch of other arrows, which is not going to be completely avoidable. Your arrows might crisscross, they just might, but it is a ways to go, okay? And you could easily just kind of come up and then take the wrong one down. So we'd like to find a better way to do it. So we're going to look at 3 illustrations of this like X mapping to only one Y. And the first one, I'll do it out horizontally first so you can see it. So we're going to take the set 1, 2, 3, and we're going to map that onto the set 4. And essentially every single one of my X's is going to have to map to a 4, just like that, okay? Because that's the only thing over there. So what we mean when we say vertically is this. We're going to set up a circle, and we're going to put all of our X values into that circle. Okay, so maybe we'll label that the X's. And then we set up another circle, and we're going to put all our Y's in that circle. You might think of it as a Venn diagram, but not really, because we do want to keep the 2 circles separate because we want to see the mapping. We're not going to union or intersect them. They are 2 totally different sets that like one of them is the starting set and one's the ending set. So we don't want it to be a Venn diagram. But now look at how the arrows look. When I do the mapping now, it's just easier to trace those arrows. Now, this is a fairly simple one here. I don't have a lot of numbers in play, but even with this, you can see how the arrows start to merge together. So if I did have something else over here and they were crisscrossing, I would have a bit of a hard time, okay, interpreting it. So the arrows just kind of go from one bubble over to the other. Now, this one is a function since each X maps to only one Y value. So here's what we mean. Just to get this definition. If I look at this X value, that X value only goes to a 4. That's it. Okay, like if you say, what does the 1 go to? The only answer to that question is 4. The 2 only goes to a 4. That's it. If I were to ask you, what does the 2 map to? Everybody answering that question would say 4. There's only one answer to that. It goes to a 4. And the same with the 3. So you might be wondering, okay, what about something that is not a function? Okay, something that is not a function. So I'm going to set this one up, and this one we're going to have a 1 and a 2 over there for our X's. And we're going to have a 4, 5, 6 over here for our Y's. And we're going to have 1 come here and like that. Okay, and there's our mapping. Okay, take a look. This is not a function since the 1 maps to both a 4 and a 5. So let's break that down. We want to make sure we are seeing this clearly. The 1, we trace where the 1 goes. The 1 maps to a 4. Okay, so we can see 1 mapping to the 4, but 1 also is mapping to a 5. And the 2 is fine. The 2 is mapping to the 6. But now, if I were to ask you, what does the 1 map to? Now there are 2 answers. Like some people might say 4, some people might say 5, some people might say both. But the point is that there's more than one correct answer for what does the 1 map to, okay? And that means it is not a function, okay? That violates it being a function. One more example here. This one, we are going to set up as 1, 2, 3, and 4, 5, 6. And I am going to change this up from what I have in my notes a little bit, just because I want you to see the arrows crossing. All right. So I have 1 mapping to 5, 2 maps to 4, and 3 maps to 6. This is a function, okay? So don't let the crisscrossing arrows throw you off. Like the arrows can absolutely crisscross, okay? It is a function because each X value is mapping to only one Y value. If I ask, what does the 1 map to? Everybody's going to say 5. What does the 2 map to? Everyone's going to say 4. Okay, it's a special kind of function. It's just known as a 1-to-1 function since each X maps to one Y And each y, I don't want to say the y's map to an x, but each y corresponds to one x. In other words, it goes both directions, that oneness. This one up here is a function because each x maps to only one y, but it's not called one-to-one because the y corresponds to more than one x. So you might be thinking, this is not a function because we kind of get used to this like one-to-one function. Well, a function can be one-to-one. All right. So if you're at a school that issues you a school laptop, sometimes those schools are called one-to-one, meaning each student gets one laptop. Each laptop is assigned to one student. Okay. And it works both ways. But this is still a function. Okay. The definition of function only has to do with each x maps to only one y. Now, let's explore the graphs some more. We want to bring this into the graphs, and then eventually we're going to bring our equations back into it, and you'll see where all of this set stuff lands us back at our algebra. Since each relation can be displayed as a graph of ordered pairs, let's look at what makes the graph of functions unique. Okay, so for this one, we're going to translate this into our ordered pairs. So -1 is mapping to a -5. So if I were to graph that, let me use a different color for this. Just the dark blue doesn't show up really well. So -1, -5, right there. 0 maps to -3. Okay. 1 is mapping to -1, and 2 is mapping to a 1. And a couple things I want you to observe. This is one that does have a pattern. So there's a pattern to how the x's are mapping to the y's. And if you've studied any algebra, you should be able to recognize that that is a line. Okay, it's a linear pattern there. And just look at the positioning of the dots there. Now, I have a question there at the bottom. Can you spot the rule or pattern that relates the x and the y? Can you spot the relationship here? Because this one does have a pattern. And you might think, oh, well, for this one, I subtracted 4. But then you look at this, and 2 to 1 definitely does not subtract 4. Now, you might do this if you're familiar with lines. If you've taken Algebra 1, maybe you're an Algebra 2 student watching this. Or maybe you're watching this at the end of Algebra 1. If you're watching this at the beginning of Algebra 1 to help you out, think of this as a sneak peek at where we're going. If you've done anything with Algebra 1, though, you recognize this as a line. And you recognize the y-intercept for that line is a -3. Okay, so it's crossing the y-axis at -3. Then you might look at the rise and the run. And you might see, between each of those points, it goes up 2 and over 1. So that would mean the slope is 2 and the y-intercept is -3. So the pattern might be 2x minus 3, that mx plus b. Okay, let's see if that works. So if I think it is 2x minus 3, 2 times -1 is -2. -2 minus 3 is -5. 0 times 2 is 0. Minus 3 is -3. 2 times 1 is 2. And 2 minus 3 is -1. And 2 times 2 is 4. 4 minus 3 is 1. And so that is the pattern. And so you might see this sometimes, that y is equal to 2x minus 3. That would be the graph there, okay? And I want you to notice that because this is where we're starting to pull what we know about graphs and lines and ordered pairs and points into this idea of mapping, okay? Like set to set mapping. Okay, so what happens if this is suddenly not a function? Okay, because I want you to see what makes the graphs of functions unique. So pretty much everything on this slide is the same as what we had before, except I picked one of the points and said, okay, we're going to violate the functionness of this. And I did that with the 2. Now, I did it with the 2 because the 2 was the last one that I typed onto this slide, but I could have done this with any of them. Okay, I could have picked the -1, I could have picked the 0 or the 1. I just happened to pick the 2. So now this is not a function. And it's not a function because I have an x value that is now mapping to more than one y value. So we have all of the same ordered pairs there. So we have -1, -5. We have 0, -3. We have 1, -1. And we have 2, 1. And now we're going to add another point. The line that I added was that one right there. And so now 2 also maps to a -1. And what that's going to do is put a dot right there. Okay. Now, here's what I want you to focus on. The thing that made it not a function, okay? What makes this not a function? Well, it's the fact that you have a 2, 1, and also a 2, -1. That's the thing that makes it not a function. You can't have the 2 going to more than one thing. So where is that on my graph? It's those 2 points right there. That's the thing that makes it not a function. Okay, if I got rid of one of those 2 points, it would be a function. Now, if I got rid of this point right here and kept this one, it would no longer be a line. Okay, it would break that pattern, but it would still be a function. Okay, the point is I can't have both of those points. All right. So I wrote on my thing a little bit. We'll clean that up. All right, so here's the key idea. If there are any vertically stacked points, vertical means like this up and down. So any vertically stacked points that are stacked right on top of each other on the graph, then the relation is not a function. If you see 2 points stacked on top of each other, it is not a function. You've got something like this going on where one x goes to 2 different y's. If there are no vertically stacked points on the graph, the relation is a function. Okay, and this rule is sometimes called the vertical line test, which your teacher might describe to you any number of different ways. I've used like meter sticks and rulers, and I think my algebra teacher when I was in school, like we used to have to carry ID cards and he would use that. Okay, so here's what we mean. If I pick any vertically stacked points, so I'm going to pick this point right here and this point right here. Okay, see how they are vertically stacked? The first point there looks like it is the point -8, 5. The bottom point is -8, 2. What that means is that in my little mapping, my -8 went to 2 different things. So vertically stacked points means it is not a function. The great news here is that this is going to give you a really quick way to determine if something is a function. If you see points stacked on top of each other vertically, it is not a function. If you do not see any points stacked vertically, then it is a function. Okay, so you don't have to go back to the map. All right, last few vocabulary words here. When dealing with functions, we have specific words we use for the 2 sets. So instead of calling them x set and y set, we refer to them as the domain and the range. Okay, the domain is all of the numbers in that X set, sometimes called the inputs, okay? They're called like the inputs because it's where you're starting, okay? You start with your input and then you get your output after you do the input. So the domains, it's not plural, domain, is all the set of, is all the numbers in the X set. That is the domain. And the range is all of the numbers in that Y set. These are really, really, really important vocabulary words. So I'm going to ask you once again, if you're watching this, you got a notebook handy, stop it, write down these definitions, highlight it. Okay. I don't usually ask students to stop a video and write stuff down, but stop the video and write it down. Domain is all of the numbers in that starting set, and the range is all the numbers in that ending set. These sets might have an infinite number of elements, such as the odd numbers. So we might say the domain is the odd numbers. Well, there's an infinite number of odd numbers. When this is the case, we want to move beyond listing them in set brackets or bubbles. Okay, if we are dealing with all integers, or I don't know, all numbers, okay, then we do not want to be listing them out. And that's going to push us to some other tools for managing this mapping. So let's take a look at this. What are the domain and range for this function? First off, I know it's a function because if I look at my x values, I'm only seeing one arrow coming off of each number, okay? Only one arrow coming off each number, so I know it's a function. But we also have this etc. Okay, and the reason these are kind of jumbled up is because technically they can be, and also because the pattern and the position of the etc. was very awkward if I did not do that. So looking at this, 1, tracing that arrow, maps to -1. 3, maps to -3. 5 maps to -5. And probably by now you can see the pattern. 7 maps to -7. 9 maps to -9. And 11 maps to -11 with an etc. In other words, it's going to keep going. So how would we describe the domain? This is the domain. This is my starting set. And looking at it, it looks like 1, 3, 5, 7, 9, 11. So I might say the domain is the set of positive. I don't know if I need to say positive. We'll just say odd numbers. They are positive, but they are odd numbers. And my range over here looks like it's the opposite of the odd numbers. Opposite of odd numbers. Okay, and so we have the domain and the range, and we're dealing with the infinite sets there. Okay, please don't forget to like this video if you found it helpful, subscribe for more math help, drop a comment or ask a question, and check out the practice set for this lesson. I'll try to link that in the space below.